Hello and welcome to the week 5 material. We are going to be looking at predicate logic, just building up some of the definitions, some of the concepts that we'll be needing. The language of mathematics is usually expressed in terms of some natural language, for example, English. And certainly if you want what you're saying to be most easily understood, it is usually much better to describe things in English. But English does have the problem that it is possible sometimes to say things that are slightly imprecise, that can be the source of misunderstandings. And if we want a language of mathematics that is going to be always correct, that we are always going to be able to agree when something is true, when something has been proved correctly, then we want something that is going to be very symbolic. Something where to be able to check whether something is true is going to be like doing a straightforward algebraic manipulation. And that is the point of predicate logic. And the rules of predicate logic have quite a lot in common with the rules of propositional logic, but there are more concepts in it, which is a good thing because it needs to be rich enough to be able to express the things that we need in mathematics. And the first thing that you start with in maths is the set of natural numbers. You can build up the set of natural numbers within predicate logic, and then you can start proving things about it. So this is what we're going to do. The other important point about having a purely symbolic language with which to express mathematics is that we can then teach it to computers. And a big thing at the moment is trying to get computers to do mathematics for us. And they can up to a point. Some very big, difficult theorems have been checked using computers. And that's because they know how to work with the sort of expressions that we're going to look at in this video. But it combines, predicate logic combines to some degree set theory and propositional logic. So we're going to see how that happens. One of the key things that we haven't had when talking about sets or talking about propositions is the idea of a variable. So this is going to be some kind of placeholder that you can then substitute for different values. So that's one kind of very important concept that we will introduce, but we'll go through it bit by bit. I think what might be useful at this stage is to give you an example of a statement that we all know very well, but written in terms of predicate logic. So one of the things that we all know very well is when you can find solutions to quadratic equations. So what is a quadratic equation going to look like generally? So I'll just write predicate logic here. And then I will immediately go and give an example. So suppose we have a quadratic equation. and it will be a general quadratic equation. So it will be, I won't tell you what the exact coefficients are, I'll just write the general form of it. So it's going to look like ax squared plus bx plus c equals 0. And we have a way of knowing whether this is going to have any solutions over the real numbers. And the way that we work it out is by calculating the discriminant. So you remember the formula, the quadratic formula, there is a bit under the square root sign. And if you want to solve this over the real numbers, you need to be able to take that square root. So you need the thing underneath it to be positive or 0. So that leads you to the idea of the discriminant. So we can solve this with some real number x precisely when the discriminant is positive. So it could be strictly positive or it could be 0, but as long as it's positive, so what is the discriminant in this case, i.e. when b squared minus 4ac is bigger than or equal to 0. Okay. So hopefully this is a reasonably intelligible sentence about mathematics, but written in terms of English. So something like ChatGPT would be able to do something with these words because it will have seen other words similarly on many websites, but it won't exactly understand them just from this. If you want to get a computer to understand it, we want to take these English words and produce something more symbolic. And this is what you end up with when you do that. And we'll get a lot of practice at working with these things, so it won't be quite so horrific as it might first appear. So this is what the statement is translated. So for all a, so this is a symbol that means for all a, b, c in the real numbers, there exists an x in the real numbers. So this backwards e means there exists, such that we can solve this equation. So this statement holds ax squared plus bx plus c equals 0 if and only if b squared minus 4ac is bigger than or equal to 0. Okay, so this is as I said, for all. So this can be translated as saying, you give me any a, b, and c you like, then I can find an x that solves this equation if and only if I know that the discriminant is bigger than or equal to 0. Okay, so that's the sort of statement that we're going to want to discuss, and we're going to build up the various parts of it and just give them some names. So let's do that. So let's let's build up the parts of this. So one thing that you need when you are coming up with a theory that you can work with is constants. You don't have to have constants, but in almost all cases you're going to want them. So we need constants. So these are just going to be we're not going to say anything about them other than they exist to start with. They're just going to be some symbols that will be important to us for whatever reason. So these are some symbols that we are going to eventually explain what they mean and how to use them. So one symbol that we have used twice in the above expression is the symbol 0. So that's an important constant. If you're doing any kind of algebra at all, you want to have a symbol for 0. So for example, 0 is a constant in the above expression. But usually we're going to want to use more than just 0 as a constant. If we're working with the natural numbers, then we're going to want symbols to represent 1, 2, 3, and so on. So in the natural numbers, we would also have 1, 2, and so on. Again, these are just some symbols so far, and this does not say anything about how they interact with each other. Just starting off with some symbols. The next thing we are going to want are some variables. We need variables. So these are going to be some other symbols which are going to be things that we can replace with constants. So things that we can substitute for. So these are more symbols that we can use by substituting in constants. Now, sometimes it's a good idea to use capital letters to talk about your variables, because sometimes you want to talk about constants without saying exactly what they are, and then you want to use lowercase letters. But I thought if I wrote all of these as capital letters, we wouldn't recognize it as a quadratic equation. So in this case, these are all variables. So A, B, C, and X we're treating them all as variables because we could substitute any real number for any one of these, and then this statement would still be true. Right, so in the above, A, B, C, and X are all variables. Okay. Now, we will talk about so one very important thing about variables is that you can quantify over them, and we've seen in the above the two quantifier symbols. One of them is for all, and the other one is there exists, and they are related in a way that we'll come back to. But before we talk about that, I want to talk about relations, functions, and operations. So relations are ways of associating some of the constants together. So relations associate some constants together. So for example, you might want to relate all of the even numbers together. So we could say x is related to y if these are purposes use a and b here. And say a is related to b if a and b are both the same parity, let's say. So if they're both even, then they'll be related, and if they're both odd, then they'll be related. So both even or both odd. So we don't do a lot of talking about relations just yet in the maths that we're doing, but it does come up a lot in future. One thing that we definitely do a lot of are functions. Functions are, I don't really need to tell you what functions are, but because you'll have seen so many of them that you could tell me, but they're basically machines that you plug in some collection of constants, and then they'll spit out another constant. So they machines that take in some constants. A lot of the time we think about the functions that we see on our calculators, and they are usually univariate functions, so they just take in one number and then spit out another one. But you can build up more complicated ones. But anyway, machines that take in some constants and spit out another, or possibly a list of other constants. So for example, sine x is a function. So you plug in something for x, then you get something out. And that's an important part of the language that we're using. Operations are very similar to functions, but it's sometimes easier to think about operations rather than functions, particularly if we want to focus on the fact that we're plugging two different things in. So these can be ways of combining constants. So for example, the operation of multiplication. So e.g. The operation A times B. Or it could be, another one could just be A times A, which we might write as A squared. Or if it's X, then X squared. And then we can also combine things by addition. Now, what happens if you apply these operations to variables is that you get things that are called terms. So from these we get terms, and I'll just give you an example. So for example, any variable is a term. So x is a term, and then I can apply any of these functions or operations to it, and then I get another term. So x times x, which I might also write as x squared, this is a term. And then I could do a times x squared. So this is a term. So is b times x. So is c times x. These are all terms. And then I can add them up. So also ax squared plus bx plus c is a term. And from terms, I can then build up formulas. So formulas are expressions which can be true or false. And in the case that we were looking at above, so for example, in the quadratic equation case, ax squared plus bx plus c equals 0 is a formula. And the reason it's a formula is because if I substitute values of a and b and c and x in here, I can decide whether this is true or not. So substituting a, b, c and x with values which are constants, I can decide whether this is true or not. Right, so in fact these are related. In fact, the reason that this formula is true or not is because it's really a relation. So you're really saying, are these two expressions that I get from this term and this constant, are they related by the equality symbol? But we have actually had another. So even in the above expression, we do have a different type of relation. So another example is b squared minus 4ac is bigger than or equal to 0. So those are two examples of formulae. When you plug numbers into it, you can decide whether it's true or false. Okay, and then we want to from the formulas to be able to get statements that are that we're making about all real numbers or about all integers, right? So this is the point of mathematics, is to be able to make statements about the mathematical objects that we find. So, are there infinitely many prime numbers? Is the square root of 2 rational or irrational? And in order to make such statements, we need to be able to quantify. So we can quantify over variables in a formula. So this is where you decide you've only got two options. One of them is for all, and the other one is there exists. So let's give an example. So there exists x. Let's take a natural number. There exists x in the natural numbers such that 2x equals 4. Okay, so this is the formula, and this is the quantified. This is the quantified variable. So this is a formula, this is a variable, and this is a quantifier. This is the existential quantifier. So what I'm doing is I'm saying something about all the possible instances, or one of the possible instances of a constant I could plug in here to make it true or false. In this instance, I've given you a quantified formula which does have a solution. Now, I've actually quantified over all the variables, so there's nothing left anymore. But in any case, I now can say that this is true. So this is a formula with no free variables, and then it's called a sentence. So it is called a sentence because it's something that you're saying about something that you're saying that can be evaluated as being either true or false. In this case, it's a true sentence. It is a true sentence because there does exist a natural number that solves this equation. Because if I put x equals 2, then the formula works. Right, the other one is for all x, or for all whichever variable you're looking at. The other example, so this is the existential quantifier. And it says that I can find some example that makes it work, whatever it is. there is some instance of the variable making the formula true. The other quantifier that we might want to use is the universal quantifier, and that is the one that says that no matter what choice of constant to replace your variable you use, it's true. So another example, for all x in the natural numbers, 2x is 4. So this is not true, because this is supposed to be saying that it doesn't matter which x I pick, this will always be true. So this uses the for all symbol, which is the universal quantifier. And it means that you can put any value in of x you like, and then you're saying that the formula is going to be true. So the formula holds for any choice of constant to substitute. So we know that that's not true. We know that if there's only one number, only one natural number that solves this. If I put in 3, it's obviously not going to work. So this is a false sentence. So this example is a false sentence. And we've already looked at a sentence which is true, which uses all the quantifiers, but let me give you another one that is true here. So I could say for all x in the integers, for all y in the integers, x, y is 0, that happens only if x and y are both 0. One of x and y is 0. So this is true if and only if x is not equal to 0, x equals 0 or y equals 0. So that would be another true sentence using the universal quantifier, which is true. So yes, if you plug in any value of x and y, then either you have picked one that is 0, and then this is true, or you haven't picked one that is 0, and then this won't be true. So we'll pick that up and then start talking about how this gives us predicates, and we can use that to check, to define sets in the next video.